Hello students, welcome to today's session. So today we are going to start with a very important chapter of organic chemistry, that is isomerism. This particular chapter in totality comes in the class 12th, but some part of it is in 11th as well. But any student who is having a little bit of understanding of chemical bonding can understand this chapter directly. So this isomerism chapter is such an important one that any simple question can be made quite difficult by introducing isomerism part into that particular problem. So make it a point, this chapter is indeed a most important chapter. It is mind opening chapter, and let us go directly into it. In today's session I shall be introducing very basic aspects. What exactly do we mean by isomerism? So I am sure about the fact that after the session you would feel little strengthened with the topic in regard to the conceptual understanding. Once the concept is clear, the other things would roll down very easily as we proceed in the upcoming sessions. So when I talk of isomerism, first we have to theoretically define what do we mean by how do we define the term isomerism or isomers. We simply plainly would say it like this, that the existence of two or more molecules having same molecular formula but different, here it is written, different bonding arrangement of atoms. When a given molecular formula can be placed into different bonding arrangement, those entities which we acquire or we get is called as isomers, or different orientation of atoms in the space. Now both of these, as my style would be, if we have defined something, let us dig deep into it and what do it exactly do we mean by it. Just if I would write a simple example here, if I just would write C4H8. Now C4H8, you can draw this C4H8 like this. If I draw it like this, you can show it like this. This is butene 1. This particular compound is called as butene 1, or you can draw it like this also. This is called as butene 2, or somebody else can show it like this also, cyclobutane, or somebody else can show it like this, methyl cyclopropane. So all of these, if I would say that this and this, all these would have same molecular formula, that is C4H8. Only difference is in the arrangement of attachment of atoms around the carbon. So basically here the double bond is at the first position, here it comes on to the second position, and the other two are not alkenes, they are cycloalkanes. But as a matter of fact, this one or this one shall then be said as to be isomers because their molecular formula is same. So this definition indeed would be now clear to all of you, that different bonding arrangement of atoms. This particular molecule I will be explaining in much more detail in upcoming 15-20 minutes. And second thing which we have defined here is different orientation of atoms in the space. Now say for example, this particular compound is called as but1ene and this is called as but2ene. Now if you go to market, and as a matter of fact this is cyclobutane and this is methyl cyclopropane. Now if you would go to a market to buy butene 2, if I simply would write butene 2, so I am thinking of buying butene 2. As soon as I reach market, the shopkeeper will show me butene 2 would be available in these two forms. And this again I am going to explain it in quite detail in upcoming 15-20 minutes. So this is available in this form, and the detailing we shall be doing it in good amount of detailing would be done for this particular molecule for your understanding. So this is available in two forms. Here what you are able to see here is this methyl and this methyl are onto the same side of the double bond. Here these two methyl are opposite to each other. So here the bonding aspect is same, 1, 2, 3, 4. The carbon length is same, the double bond is between second and third. Here also 1, 2, 3, 4. The double bond is between the second and third carbon, but the orientation of atoms in the space are different. So these are also called as isomers. Very soon we will be defining these as to be stereoisomers. So first aspect is very clear. We have understood the meaning of isomerism or the definition of isomerism. Now here, before I go into the detailing of this particular topic, I just would request you all to see this particular series of class 11th organic I uploaded some time back, Balle Balle Organic series. In that, I just would want you to see into these two sessions, because if you come prepared with these two sessions, upcoming sessions you would feel comfortable with in the topic of isomerism, the bonding aspect required in the organic chemistry, and this is the most important. Although while discussing isomerism, I shall be explaining degree of unsaturation once again, but if you want to understand it in length, I would be placing the link of these two videos or these two sessions onto the description box. You can see into that. So degree of unsaturation and chemical bonding, this aspect is the most important. Now coming back to the topic. Now if I have to now go into the detailing of isomerism, when we talk of isomerism, this can broadly be classified into two categories. One, we call it as structural isomers or isomerism, or constitutional isomers or constitutional isomerism. And second is stereoisomerism. Stereoisomerism is also called as spatial isomerism or stereo. The term, if I would say stereo belongs to term called as space. Anything in space is said as stereo. Now, as we have to understand both of this in length, what do we mean by structural isomerism and stereoisomerism? But before I go into that, let me classify these further. This particular structural isomerism may be classified into number of things. This also can be classified into two categories, and then we will understand all of these classifications in detail. So structural isomerism can be further divided into position isomerism. Then it can be chain isomerism, then metamerism, then there can be functional isomerism, then most important, which would go in length, is tautomerism, and then many books would write chain and ring isomerism, and there can be one to more types which can further be defined into, which we will see as we proceed. Now stereoisomerism can be of two types. One, we call it as conformational isomerism, and second we will see into configurational isomerism. Today in this particular session, my endeavor is to let you know the conceptual understanding of structural, stereo, configurational and conformational. Once you are clear with it, then the chapter becomes, or it becomes very smooth, and configuration can further then be divided into you can say geometrical isomerism, which we will see in a upcoming session, and optical isomerism. Now, as my style would be, we have to understand isomerism definition we have understood. Now we have to dig deep into the topic of structural isomerism and stereoisomerism. What do we mean by those? Because I have seen with my experience, number of times people have done entire of isomerism, but they are not very clear with the basic understanding. When we ask ourselves what is the basic difference between structural isomerism and stereoisomerism, what is the basic difference in it? The basic difference you would find is, generally you miss this point at times. The basic difference, when I say if I will place 2-3 compounds in front of you and I would say that these are structural isomers to each other, then what is the basic difference you would see? The IUPAC names are different. Wow, this is very important, very important. IUPAC names of structural isomers are different. Why? Because the fact is, these are being made by arranging atoms in the bonding arrangement of different atoms has been changed for a given molecular formula. And whereas in the stereoisomerism, what you would able to see, those entities which I am defining it as stereoisomers, they would have same IUPAC name, same IUPAC names. They would have same IUPAC names. At times, this basic understanding is not clear with. Let me define what I just have said. Because in the definition we said different bonding arrangement of atoms. Different bonding arrangement of atoms are in this site. If you see butene 1, butene 2, cyclobutane, methyl cyclopropane, these would fall under the category of structural isomers because the bonding arrangement has been changed. But when you talk of different orientation of atoms in the space, here the IUPAC name is same. This also is butene, this also is butene. So both of these are butene. Only difference is very soon we will be defining it as this is said as cis, this is said as trans. Why is it so? We will be answering it. But the IUPAC naming is same. Cis and trans we have said because we just want to distinguish them from each other from the stereochemical point of view. Okay, so let me come back to the topic. So structural isomers are those which would have different IUPAC name, and stereoisomers would have same IUPAC name. Their IUPAC names would be the same one. Now the point is that if I now further define this, because this get further classified, and this structural isomers can be of many types, chain, position. As we proceed, I let you know chain, position, functional, tautomerism, and all of these. All those isomers would have different IUPAC naming. Now coming on to the stereoisomerism. When you talk of stereoisomerism, we can classify this into two categories: conformational and configurational isomerism. As we have shown this flowchart earlier also to you, here I have said stereoisomerism can be of two types: conformational and configurational. And that configuration further get classified into geometrical and optical. Now again, the basic understanding. What do we mean by, what is the basic difference between if I talk of conformational and configurational? How these two are, get distinguished from each other? If I would place 2-3 things in front of you, how could you say that these two are configurational and these are conformational? For that, you have to have the understanding which I am going to let you know in a minute's time. Now, when I say conformational isomerism, when I say two entities, say for example A and B are in front of you, two structures are in front of you, and both A and B are having same IUPAC names, because that is the very definition in organic chemistry. When you talk of stereoisomers, they would have same IUPAC name. Okay, and how then they can be distinguished? By putting some prefix in front of you, just like in the case of butene we wrote cis and trans, and as we proceed we will do lot of such prefixes: cis, trans, syn, anti, then dextro, levo, rs. There are number of ways to distinguish one configuration from the other one. Now coming back to the point, when I say A and B are if I say A and B are said to as conformers to each other, then what is the condition to be met? These would be said as conformer to each other if their interconversion of A to B, structure A to B, and then the interconversion of B to A did not bring any bond breakage. If you would not do any bond breakage, what I am trying to say, there is a structure A and structure B, both are having same IUPAC name, and I am saying they can be said as conformational isomers to each other only if I convert A to B or B to A, there is no bond breakage taking place. Then that entities would be said as conformers. Let me explain what I am trying to say in a minute's time. Now, if I would simply take an example of, let me take 1,2-dichloroethane, or you can take simple ethane as well. Okay, let me take, I have already written dichloroethane, so let me take this example. So this is 1,2-dichloroethane, and in this carbon is sp3 hybridized, and this is a simple Lewis dot structure which we have drawn, but it is not showing anything about the 3D structure. This carbon is sp3, and since it is sp3, so So then it is supposed to be tetrahedral. It is supposed to be tetrahedral, and it is tetrahedral in fact. Now, how do you show a tetrahedral in a 2D slide? How could I show it? So I can show it like this, that if I will say this is the carbon, and this dark wedge which is being shown here, if I would say this is coming out of the plane of this particular slide, and these dotted lines are going into the plane of the slide or plane of the board. So this is coming out of plane of board, coming out of plane of board or plane of slide, and this is going into the plane of the board, going into the plane of the board. And this line, the simple line which is there, this is on the plane of the board, on the plane of board. So what we are saying, this particular line is on the plane of the board, and this dark line is coming out of the plane of the board, and this is going into the plane of the board. Now if I just would draw, this would show you, if I would mark it here, this definitely would give you a feel that it is a perfect tetrahedral. So this shows you that it is a tetrahedral arrangement. Now in this tetrahedral arrangement, if I just would write CH4, say for example, so H is here, H is here, these two hydrogens are in the plane of this particular slide, and this H is coming out towards you, and this H is going into the plane of the slide. And in a way, it is showing me perfect tetrahedral. All angles are 109.5, and to be precise 109.28 minutes. So this is perfect tetrahedral which we have got. Now what we have to show, that this carbon and this carbon are perfect tetrahedral. So how could I show you? So if I just would write once again for you, this is the structure which we are supposed to draw. This is the structure which we are supposed to draw, and this is the first and second carbon. So if I would say this is the first carbon, this is the second carbon. On one side you have chlorine, this is chlorine, and two are the hydrogens. So I drawn this particular part, and similarly if I would say there is a chlorine and this is hydrogen and hydrogen, so I have shown the other part also. Now between carbon there is a single bond. Now you can very well feel that if I would see this molecule from this direction, what I am able to see is there is a chlorine here. So behind this chlorine you would find this chlorine. So I will say, and behind this hydrogen you would find this hydrogen, and behind this hydrogen you would find this hydrogen. I think I made my point clear. So what I'm trying to say here is, this is a 3D structure of this particular compound, and in this 3D structure, if you would rotate this carbon-carbon bond, you can definitely rotate a carbon-carbon single bond. And if you rotate the carbon-carbon single bond, there could be a situation created whereby, if I would say this remains as such, and the bottom carbon, the carbon which is in the lower side, if I just would rotate it, I may get this sort of a structure as well, isn't it? I may get this sort of a structure as well. In the process, I can say here there was a chlorine, hydrogen and hydrogen. Now what I did, I almost have rotated it by 180 degree. I rotated it by 180 degree. As a consequence, this chlorine now would come opposite to this. The green chlorine and the pink chlorine now has become distant apart. So how much angle I have rotated with? And during this rotation, I never have broken any bond, nor I have made any bond. I just have rotated it. But after the rotation, what I have felt is that this particular, which we will be discussing this in detail in conformational isomerism. Here I am just giving you a trailer of the entire, I am showing you the trailer of the picture. So here what we are saying is that this chlorine and this chlorine, as has become distant apart, we will be saying that it is more stable because the electronic repulsions are less. And here I will be saying comparatively this particular one is less stable. And this less stable, later on we will be saying it as to be eclipsed conformer, which I just don't want to introduce at this point of time. But anyhow, this is called as eclipsed, and this later on would be said as staggered conformer. Here, my endeavor is to let you know that during conformational isomerism, I never have broken any bond. I just have rotated the molecule such that a new arrangement you would, because now if I would say, it is just like I used to say this a lot number of times in my regular sessions, that conformational isomerism can be applied on us also. I'm at this point of time, I'm sitting in front of you, but when I want to drink water, I can move while I was walking, or while I'm sleeping, or I'm doing so many things in a day. When I'm doing so many things in a day, none of my bond get broken. My fingers are intact, everything is the same. But while I am sleeping versus while I'm standing, in which posture I would be more stable? Obviously, when I'm in the resting mode, I will be more stable. Same is the case in this case also. If you talk of dichloroethane, 1,2-dichloroethane, it can rotate, roam around in different number of ways, but it can roam in the room in the form of eclipsed or in the staggered form. So we later on would see that staggered form, a given molecule tend to become more stable in the staggered form rather than in the eclipsed form. So this is the beauty of the thing, that different conformers would have different energy, and when they have different energy, their reactivity gets changed while doing any chemical reaction. And conformational isomerism can be applied on us also. When I'm walking, when I'm talking, when I'm resting, when I'm drinking, in different forms, I would have different conformers assigned to my body, and in different postures I am having different amount of stabilities, because in none of the posture any of my leg, hand, or any bond get broken, isn't it? So this way you can relate it with the daily routine example as well. So let me come back to the topic. So conformational isomerism are now is very clear to you, that when I am saying A and B are conformers, then what we shall be saying, that they can interconvert from each other without without any bond breakage. So you do not require, so this is to be highlighted once again in bold. So did not bring any bond breakage. So if A converts to B and B converts to A without any bond breakage, then we shall be saying those to be conformers. Coming on to now configurational isomerism. So now you should have got an idea that how it could be different from the conformational. So very simple. A and B can be said as to be configurational isomers if their interconversion from A to B or B to A require bond breakage or bond cleavage. Bond breakage and then bond what I should say, makeage. this I don't think is a word in English, or I would say then bond making. So you need, so if A and B, again these two structures would have same IUPAC names, but conversion of A to B or B to A requires bond breaking and then bond making. So if that requirement is seen there, then I shall be saying that two entities would be said as configurational isomerism. Now let me explain the example which we took few minutes back. This particular form butene 1, so we also have defined butene 2 bond line representation, and then we said it can be available in this form or it can be available in this form. So these are the 4 structural isomers we have drawn for this, because all of these 4 have different IUPAC names. Now if I would dig deep into this, as I said, this can be available in market in 2 forms. Now here my endeavor is not to let you know that in which classification this would fall. First endeavor of anybody should to understand what do we mean by configurational isomers. Now I'm saying this particular entity, if we want to define, or if we want to see how they would be available in different configurations, to understand that we have to go into depth in terms of its bonding or arrangement in the space. This carbon is sp2 hybridized, this also is sp2, and this is CH3, this is CH3. Let me draw it in this form also. So this is the molecule. Now in this molecule you have to be very clear with the fact that this is sp2 sp2. Now when these two are sp2, these must be trigonal planar, and this is sp3, so this must be tetrahedral. Now first we have to see this molecule in space, then only you can understand it well. Now for your understanding, I have already drawn. So this is the carbon and this is the carbon. Okay, so these two are the carbon which I have shown it, and let me show with another color, CH3 CH3, and here you have one hydrogen along with it. So there is hydrogen as well as a double bond. Now what I can do here is that if I just would say that there is a hydrogen here and there is a methyl here, is it okay? And this is methyl, and similarly this is a methyl here and this is a hydrogen. Now where do you see a pi bond? A double bond is consisting of a pi bond which is perpendicular to the molecular plane or perpendicular to the sigma bonds. So this is the pi bond which you have, and this pi bond is being formed by sideways overlap. I hope you all know this fact that this is being made by sideways overlapping. This is made by sideways overlapping. So in if I have to draw it in a speedier way, that how could I show you that this is the carbon, this is the carbon, there is a pi bond here, there is a pi bond here, these are being joined to each other, or these are attached to each other with pi bond. And now what else you have with you? There is a hydrogen and methyl, this is a hydrogen and methyl. Now here you have to understand one fact, that hydrogen and methyl, which I have shown you with the orange marker, they are in the same plane as that of a sigma plane of carbon-carbon bond. So they are into the same plane, if you could see it well. Okay, so let me draw it once more for you. These are in the same plane. Is it okay? And this also is in the same plane. Is it okay? So the carbon-carbon and carbon-hydrogen are in the same plane. Although this carbon is tetrahedral, if I would show you a bit more in detail, so this can be shown it like this. So one hydrogen, and there is a, or you can, if you want to show it like this also, you can show it like this. There is a hydrogen, and this hydrogen could also be in the same plane, but these two hydrogen would not be in the same plane, so it is tetrahedral. So we have this sort of detailing we will definitely be doing when we will be explaining this in detail. Here my endeavor only to tell you is that there is a carbon-carbon bond, and that carbon-carbon bond between the second and third carbon is a double bond which is being attached with a pi bond. Or simply I want to say it like this, that this is the pi bond which is making this carbon-carbon bond rotation little restricted with, it cannot rotate because these are in the horizontal plane with 120 angle. This I should have marked it, although it doesn't look like 120, because when you see it from here it would look like 120 because I am showing you in the horizontal plane. So this bond cannot rotate, unlike the single bond, because it is being bonded to each other with a pi bond. Now let us go into the depth. Now the point here is that if I would say to you that this particular thing, there is a pi bond here, there is a pi bond, and this is attached to each other, fair enough. And now I just would place hydrogen methyl. So two methyl groups are onto the same side towards you, it is coming towards you because it is in the horizontal plane, and two hydrogens are going into the plane of the copy or plane of this particular slide. Now if I just would want that this hydrogen and methyl would remain at the same position, but I just want that this methyl and this hydrogen would swap their positions such that this should become like this, such that it should become like this. How could I do this? Would it be possible or not? So to do that, what I just have done, keeping this pi bond as such, this should remain as such. Would it be possible? Can I interconvert them? Now here we have to understand it well, because once you want to go from this side to this side, just to replace methyl with hydrogen, or just to swap methyl with hydrogen, what you need to do? First you need to break this bond, because there is a bond here. You have broken this bond. Once it got broken, then you rotate it. Then this carbon-carbon bond is to be rotated. This carbon, once this pi bond has been broken, then this carbon-carbon bond has to be rotated, such that now what would happen? This would go into the horizontal plane. And now, because what you have done, this hydrogen is there, this methyl is still there, and what you have done, this hydrogen and methyl, you just have rotated upward. If I would show you like this, you just have taken this towards up, and this has gone to the bottom. As a consequence, this hydrogen comes. So are you able to understand what I have just drawn? And now, so first I go to this side by bond breaking, and now just twist it once again such that this pi bond is again made. Just I brought it here and rotated it like this. As a consequence, a pi bond is again regenerated. So definitely you can go from this direction, from A to B you can go, and from B to A you can go, but that interconversion requires bond breaking and making. I hope you have understood this viewpoint of mine. So what is there? There is a pi bond. Just see here, there is a pi bond. I just have rotated, keeping one intact. I just have rotated, and when I rotated it, one pi bond get broken, such that this hydrogen and methyl get interswapped their position and then remade their pi bond. So this type of isomerism which we got is said as to be configurational isomer. So we shall be saying this has to be butene 2, IUPAC name is same. For this also the IUPAC name is same, butene. But the point here is, what is the difference? How can I say these two are different in the sense theoretically? So we shall be saying this methyl and this methyl are on to the same side. So we will be saying cis, and this methyl has gone opposite to each other. We will be saying trans. So how this is a theoretical way of assigning it cis trans. But how actually scientists have get to know that these two are two different configurations? Because they get to know it from the fact that they do have different melting and boiling points. Their chemical reactivity is different towards the different reagents. So as a view, because their melting and boiling point, their dipole moments are different, we are able to analyze that they would be having different, they are the part of different configurations. So I hope you have understood. Now the point is that if you go to market to buy C4H8, these all would have different IUPAC names, so they do have different physical and chemical properties. But this butene has two configurations, and that two configurations get distinguished from each other from their melting and boiling point. So I think I made my point clear. So this viewpoint where you are not able to rotate the bond because of the fact that there is a pi bond and bond breaking and making is required, this later on would get classified into the category of geometrical isomerism. And make it a point, just see it from the holistic point of view. It is not that this isomerism would come here only. In the later on in the coordination chemistry also, you happen to see this sort of different configuration. Just like if I would show that there is a complex of this type, platinum ammonia twice Cl2. This is a square planar complex, and this square planar complex is available in two forms in the market. So if I because this is a square planar complex it is. So just see it from the totality, that if I just would write ammonia as a ligand here and chlorine here, now just you swap in such a way that now ammonia and this Cl and this Cl. So this interconversion also requires bond breaking and making. You cannot simply just, and make it a point, these are not any bonds. These lines are just, I'm showing the square planar arrangement. These dotted lines are just, these are just actual bonds are these. These four are the actual bonds. So this also would get classified later on the category of cis and trans. So this, make it a point, the isomerism which you are understanding here, you have to view the molecule in 3D. If you start seeing the molecule in 3D space, wherever the isomerism would come, whether organic or inorganic, your thinking or your concept clarity would be crystal clear. Let me take one more example and then finish today's session. Now, this particular compound is called as lactic acid. Now, this particular lactic acid, if you just would see, this particular carbon is sp3 and is tetrahedral. So, if it is tetrahedral, I can show it like this. If I would mark it like this, this is a tetrahedral. So, this is COH on one side, this is the central carbon, and on one side you have CH3, and other two things you can take anywhere, H and OH. Now, this lactic acid, when when we have seen this lactic acid, we never found that it would have a this again I'm going to explain. This particular molecule again would have different physical it would have some configurations. It is available in nature in two forms. Now the point is that here in this categorizing this particular entity, we shall be classifying this into the category of optical isomerism. Optical isomerism again is a part of configurational isomerism, which we have explained somewhere above, where I have shown, yes, here it is. So here I have said configurational isomerism falls under the category of geometrical and optical. Geometrical isomers can easily be distinguished from each other from the viewpoint of their physical properties, like melting and boiling point and things like that. But the point is, there are some configurations which that configurations cannot be distinguished from the physical properties or from the daily chemical reaction, regular chemical reaction. So there comes the role of optics. Now, have you ever noticed or thought it like this, or you have read it earlier also, why optics or optical isomerism why optics comes into the topic of isomerism? Because there are some configurations which tend to show different behavior to the light. One configuration takes the light to the positive side, another configuration, same molecule but in different configuration, takes the light into a different direction. So that way, with the help of light, we are able to distinguish some compounds which would have configurations available, but otherwise from the physical and chemical properties it is very difficult to distinguish them. So there comes the role of the light. Now, as a matter of fact, this particular lactic acid has a carbon which is joined to 4 different groups. As a matter of fact, here, although we will be doing it in detail, such carbon which is attached to 4 different groups or group of atoms, that particular carbon is called as chiral carbon. Chiral carbon is a carbon which tend to get attached to 4 different atoms or group of atoms, and what basically is chirality and things like that, we will be doing it in detail in optical isomerism. Here I am going to explain this. Just don't see it from the optical isomerism, just see it from the viewpoint this way, that this molecule is available in nature in 2 forms, which are configurational isomer, and their interconversion also require bond breaking and making. So my endeavor is to tell you the concept first. Now see here. Now if I would say I have with me this molecule, so in this molecule what you are able to see, that if I watch this molecule from this direction, this OH and H are coming towards me, or they are towards me. Now if I just would place a mirror in front of it, how does it look like? It would look like somewhat like this. This H here, OH here, COH here, CH3 here. And at times I have seen that students have done entire of optical or isomerism, but they are not very clear with the fact that how these two are different from each other. I'm saying both would have the same name, optical, both of these are lactic acid, and IUPAC name is also same, but from the configurational point of view they are different. Now how I am going to explain it to you, how they are different. Now just watch it with me. Now if I just would pick this carbon-carbon bond and just would rotate it such that I just want to rotate it in such a way that this COH comes here in top of it and this CH3 would take this position. Now in doing so, if I do so, what I am going to do is, let me draw it along with, otherwise you would not feel it, what I am trying to say it to you. I am saying it this way, that I just would want to convert this particular molecule in such a way that this would have COH, COH, this group comes in, gets superimposed on this, and this methyl gets superimposed on this. Now for doing that, I just have rotated this carbon-carbon single bond. I just have rotated carbon-carbon single bond in this direction. Say for example, in this direction I have rotated such that this methyl would come here and this COH would come here. Now you are able to understand, or you are able to feel it with me, that when I rotate this in such a way that this CH3 would come at this position, then obviously this OH, now you have to remain with me, this OH which was coming towards me now will go into the plane of the board, and this H which was behind the plane of the board would come in the front, because you just have rotated it in such a way that this methyl went to this side by 180 degree, isn't it? You just have rotated it by 180 degree, because now this methyl is exactly in opposite direction and get superimposed on this methyl. So now in doing so, now you would see that these two are not same, isn't it? Wow, I just would write wow. Whenever I take up this topic, I feel myself again enthralled with that this COH and this CH3 when get superimposed onto this one, then I found that this H and OH are not exactly onto the same position. This H and OH now would have a different orientation in space. Definitely I can convert this into this or to this into this, but for that I have to break these bonds. First I have to break this bond and this bond, and then swap it, and then rejoin it or remake it. So this means these two are different configuration, and very soon in the optical isomerism, so the chapter is very, very interesting. Very soon we will be saying this has to be dextro-rotatory and this has to be levo-rotatory, or because physically or theoretically we cannot say this can be dextro, then this would be levo. So that means if this rotate the light to a positive direction, this would rotate into negative direction, or vice versa. That we will get through the experiment. So lactic acid would be available in two configurations, and these two configurations are showing are interacting with light. So we later on we will be saying these are to be said as to be optical isomers, and they are optically active, and later on we will be defining these as to be enantiomers. Now here I think I made my point clear. I almost have touched the conceptual understanding of all the topics, that what is structural and stereo. Structural would have same IUPAC name, all these different IUPAC name, position, chain, metamerism, which we are going to discuss in the next class, where we would find that all of these who would fall under the structural or configuration would have different IUPAC name, and in the stereo all would have the same IUPAC name, but their orientation in the space are different. And when you talk of conformation and configuration, this is the most important point. Conformational can be converted to each other without breaking, making bonds, whereas configuration you can convert one configurational isomer to the other with bond breaking and making. And then later on they do fall under the category of geometrical and optical. Who would fall under which category we will see into, or just a tip to remember that the configurations which are not physically from the physical properties, we are not able to distinguish them. With the help of light we are able to isolate them, then they would fall under the category of optical isomerism. Thanks a lot. Hope you have enjoyed today's session, and if in case you liked the discussion of today's session, because this is the first session, I am looking forward for your positive comments and your motivation, because more you motivate me, I would be more regular in placing these videos. Let us first cover the organic of 12th class, and very soon I shall also be placing the pending topics of organic chemistry of class 11th as well onto the channel. Thanks a lot. Do share it with your friends and juniors, so that we could make a community of chemistry loving people. Thanks a lot. Have a nice day. Stay safe and take good care of yourself. In the next session, we shall now be starting with the classification. Thanks a lot. Have a nice day.